Hi there, I'm Jessica Cartwright. I was a PhD student at the National Oceanography Centre in Southampton, and I'm now working for Spire Global. I'm going to be presenting my PhD work here on the use of reflected signals of opportunity as observations of the cryosphere. My PhD work here focuses on global navigation satellite systems reflectometry. This is the use of reflected navigation signals, such as GPS, to characterise the reflective surface. You can see here the R receiver picking up multiple signals at any one time. In our case, this was up to 4 at once from TEP Demosat. These are examples of the type of data that we receive from these reflections. These DDMs, or delay Doppler maps, are the maps of scattered power in both delay, time, and Doppler, distance in front or behind the spaceborne receiver. The CDDM here has a very scattered power due to the comparative roughness of the surface, while the reflection from the sea ice shows up as a sharp peak, and that of glacial ice a weaker reflection raised up in the delay domain. So why do we love GNSSR? It has much of the higher sonar and spatial resolution expected of active techniques, but as it only requires a receiver in space, it is much lower power, cheaper, and because of this lends itself to constellation missions. This in turn allows the spatial and temporal resolutions of the product to be increased due to the sheer number of measurements. It also has a very small footprint over ice, which is great for increasing the knowledge of these dynamic areas. Here you can see the DDMs from the 3 different surfaces shown earlier and how they translate into their waveforms. This is effectively a cut down the zero Doppler line of the DDM, giving a change in power with time. The glacial ice DDM on the left has a very low peak, barely visible, but very early in the delay window, arriving at -18 chips, so that's before it was expected due to the height of the glacial ice above the ellipsoid. The sea ice waveform is very high in power and steeply sloping, and the CDDM displays this classic horseshoe scatter that we expect from the rougher surfaces and that translates into this more gently sloping falling limb on our waveform. As we saw in the last slide, the change of the peak in the delay domain allows the calculation of the height of the surface. And that's exactly what I've done here. On the left is a digital elevation model of Antarctica, and on the right, the Greenland ice sheet. The most exciting part of this slide is that we're not subject to the same orbital constraints of other satellite altimetry, and therefore we can get observations over the South Pole itself for the first time, so no polar hole here. Here I've compared with a number of different DEMs at the bottom, which can be seen fully in the paper referenced at the end. These calculations have been carried out without any atmospheric corrections, and without correcting for penetration into the snow and ice, so we think it's quite impressive that we can get so close to these purpose-built altimetry missions. Now on to the sea ice detection. You have seen in the data earlier that the reflections from the sea ice differ greatly from that of the rough ocean surface, so it's just a case of quantifying that really. Here's an example of 1 month, the closest I could get to the Antarctic maximum within the extent of the satellite's mission, and compared here with the ESA CCI product. But there are full results in the paper referenced at the end, and it's actually been compared with quite a few other products, I think 3 or 4 in total. And here the results are visible on a seasonal scale, with the increase, light blue, and the decrease, dark blue, of the sea ice extent strongly visible here in the Antarctic data, and in the Arctic too. Obviously, opposite seasons, the other way around, which is exactly what we want to see. So there we are. Thank you so much for joining me on this whistle-stop tour. If you'd like to know any more, please do check out the references here, and I'd love to try to answer any questions that you have for me. Thank you!